For part D of this problem, it's again important to remember the units of our rates here. So part D says, a different procedure is used to administer the medication to a second patient. The amount in milligrams of medication of the second patient at time t hours is modeled by the function y equals b of t, and it satisfies the differential equation dy by dt is equal to 3 minus y over t plus 2. And remember that since the y is in terms of milligrams, this rate or differential equation, the units are milligrams per hour. And it gives us initial condition of t equals 1 and the milligrams or y equals 2.5. So the question asks, is the rate of change of the amount of medication in the second patient increasing or decreasing at t equals 1? So is the rate of change increasing or decreasing? Well, what this is saying is, this is asking about the rate of change, increasing, decreasing, or the change of change. The change of the rate of change, which is the second derivative. Okay, so it is important to recognize that first. Once we recognize that we are being asked for the change of the change, we need to then differentiate the derivative to get the second derivative. So when we differentiate the second derivative, we get d squared y over dx all squared. The derivative of 3 is 0, minus, since this is a quotient, we need to use quotient rule, so I'm going to differentiate the y to y prime times t plus 2 minus y times derivative of t plus 2 is 1. And that's all over t plus 2 all squared. Put that in square brackets. So one thing that is important to recognize here is that we have an embedded y prime. That embedded y prime is expressed in the red above. There's two ways to deal with this now. What we could do is we can just evaluate, figure out what that y prime is, or the dy by dt for the initial condition that we're solving for. So we can just say dy by dt when x is 1, y is 2.5. We can just put that into the original dy by dt equation. So we get 3 minus y is 2.5. T is 1, so 1 plus 2. So we end up with 3 minus 2.5 over 3 is going to end up being 5 over 6. So that simplifies to 18 over 6 minus 5 over 6. We get 13 over 6. And this is a derivative milligrams per hour. Okay? And what we can then do is we can take that value and replace it we can replace the y prime in there, because what we're looking for is the rate of change, the change of the change, okay, the second derivative, and for the initial condition of x is 1, y is 2.5. Well, we know that we have the y prime value at 1, 2.5. So replacing that y prime, I can replace that y prime with 13 over 6, and then do the rest, replace the t equals 1, y is equal to 2.5 times 1, so it's just going to be 2.5, and that's going to be all over 1 plus 2 squared. Well, I can actually evaluate this the second derivative. So calculating this out, we're going to end up with 3 times 13 over 6, which gives us 13 over 2, minus 2.5, which I'm going to write as 5 over 2. And that's all over the denominator of 3 squared, which is 9. And again, we want to make sure we're keeping track of that negative because that's going to be relevant to the problem because we're looking for whether the second derivative is positive or negative. So 13 over 2 minus 5 over 2 is 8 over 2 or 4. So we end up with our answer of 4 over 9, and that's going to be in milligrams per hour or hour squared. So since the rate is negative, and I'm just going to highlight this, since the rate is negative, we know that this is decreasing. So the rate of change is decreasing. So we say it's decreasing.